Hello everyone, and welcome to the Mathematecher channel again. In today's video, we would like to find out the rest of the Euclidean division of the sum 1 plus 3 plus 3 square plus so on until 3 to the power of 2011 over 7. So, before we dive into this, let's have a quick reminder about geometric sequences. So if we have a sequence un, which is defined in an underset of the set of the natural numbers n, that we can note capital A, such that there is a real number r, so that for every natural number n of the set capital A, the term un plus 1 equals r multiplied by the term un. Then the sequence un is called a geometric sequence of reason r, and any sum of its terms such as um plus 1 plus so on until un would be equal to the product of the first term, which is by r, to the power of n minus m plus 1, which represents the number of the terms in this sum, minus 1, all over r minus 1. Let's now get back to our question. Let's note the sum, 1 plus 3 square plus so on until 3 to the power of 2011 as capital S. We notice that the ratio between any two successive terms of this sum is always equal to the constant number 3. So this is a sum of 2012 terms of a geometric sequence of reason 3, that according to our reminder would be equal to 1, which is the first term, multiplied by 3 to the power of 2012 minus 1 all over 3 minus 1, which equals 3 to the power of 2012 minus 1 all over 2. Let's keep this in mind and determine the rests of the Euclidean division of 3 to the power of n over 7. So, we have 3 to the power of 0, which equals 1, is congruent to 1 modulo 7. As for 3 to the power of 1, it is congruent to 3 modulo 7. Then, 3 to the power of 2, which equals 9, is congruent to 2 modulo 7. After this, we have 3 to the power of 3, which equals 27, is congruent to 6 modulo 7. Then, 3 to the power of 4, which equals 81, is congruent to 4 modulo 7. As for 3 to the power of 5, which equals 243, it is congruent to 5 modulo 7. And now, when we calculate 3 to the power of 6, we find that it equals 729, which is congruent to 1 modulo 7. So 3 to the power of 0 and 3 to the power of 6 have the same rest of their Euclidean division over 7. This means that the rests of the Euclidean division of the powers of 3 over 7 form a periodic sequence of period 6. And, as we can see in the table that appears, if n is equal to 6k, then 3 to the power of n would be congruent to 1 modulo 7. As for the other periodic values of n, the rests of their Euclidean division over 7 are 3, 2, 6, 4, and 5. So according to this table, as 2012 equals 6 multiplied by 335 plus 2, then 3 to the power of 2012 would be congruent to 2 modulo 7. And as 1 is congruent to 1 modulo 7, we would have 3 to the power of 2012 minus 1 congruent to 2 minus 1, which equals 1 modulo 7, which mean that 3 to the power of 2012 minus 1 is congruent to minus 6 modulo 7. Therefore, the ratio 3 to the power of 2012 minus 1 all over 2 would be congruent to minus 3 modulo 7. And this last congruence we reached means that the ratio 3 to the power of 2012 minus 1 all over 2, which equals our sum capital S, is congruent to 4 modulo 7. Therefore, the rest of the Euclidean division of the sum 1 plus 3 square plus so on until 3 to the power of 2011 over 7 is 4. As always, thank you for watching. Subscribe to the channel if you're new to it, like the video, and until the next one, have a great time.